let's see the property of orthogonality of circles connected with radical axis. This is one of the most important geometrical property identified in the branch of connecting the radical axis of two circles. Say for example, I have two circles S dash equals 0 and there's another circle S double dash equals 0, and then I want to find the equation of the circle which cuts these two orthogonally. So geometrically we identify that if there's a circle which cuts this and this orthogonally, then equation of this circle which cuts this orthogonally, S dash and S double dash, is said to be identified. Say I have this circle with equation S equal to 0, then the geometrical property identified out here is that the center of this circle lies on the radical axis. If there's a radical axis for the two circles, which is this is the radical axis for S dash and S double dash, then using this radical axis we identify that the circle which is orthogonal to these two circles has its center on the radical axis. So this is the property. Center of the circle S equal to 0, C, lies on the radical axis of S dash and S double dash equal to 0 is the property which is identified out here. The center of the circle is nothing but a point on the radical axis of the other two circles, where my S is x squared plus y squared plus 2gx plus 2fy plus c equals 0 and my S dash is x squared plus y squared plus 2g dash x 2f dash y plus c dash equal to 0, and my S double dash is x squared plus y squared 2g double dash x plus 2f double dash y plus c double dash equals 0. That's how we identify the geometrical property connecting the radical axis with the center of the circle which is orthogonal to this and this. Now let's see how radical axis acts as a bisector, that is as the midpoint. So radical axis sometimes acts as the bisector in the case where, say for example, I take two circles and then I have this with center C1 and this with center C2, then clearly I have the radical axis exactly in the middle. Now this being the radical axis, now clearly the property says that if I draw a common tangent this is the common tangent, then the property says that the radical axis bisects the common tangent. That is, if this is the common tangent where I have P is this, and let me say it makes point of contact A with circle C1 and point of contact B with circle C2, then this will be equal to this. That is, the radical axis as bisector states that. So therefore, here my PA is equal to PB in case of the radical axis. So the property says that if I have two circles where the radical axis is drawn, then if one of the common tangent is taken, then the radical axis bisects that common tangent. That is, PA will be equal to PB. But the condition here is that common tangent is assumed to be not perpendicular to the line joining the centers. We assume that this line is not perpendicular to this common tangent is not perpendicular to the line joining the centers. If it is perpendicular, then we don't have the property which can be proved. So this is the limitation where radical axis acts as bisector with PA equal to PB. Now, not only that, this common tangent, we know that when two circles are disjoint, we have four common tangents. Say if I have the tangent this, then in this case also we have Q where this is equal to this. That is, I have this equal to this. And similarly, if I take the other tangent, then this will be equal to this. And then finally, the fourth is this. And here also we have this equal to this. So each of the common tangents will bisect, or the radical axis bisects each of the common tangent. There are four common tangents. So this equals this, and this equals this, this equals this, and this equals this are the four types of bisections which we identify through the radical axis out here. So radical axis bisects the common tangents. Now let's see one of the property where I can connect the circle with radical center and length of tangent. So let's see how we can connect the radical center and length of tangent in understanding or identifying the geometrical property involved connecting radical center and length of tangent with the circle. Say for example, I have three circles, 1, 2, and 3, which are not collinear. That is, this is with center C1, center C2, and center C3. Now we know that the radical center for these three circles is the point of intersection of all the radical axes taken in place. So I take these two circles, I have the intersection which comes somewhere in the middle, and this is the radical center which we have discussed in the previous session. Now if I just have from radical center, if I have the length of tangent, that is from here each of the tangents are equal, this, and this are equal, then if I take the measurement of this length of tangent from here, here, and here, the point of contacts, I can draw a circle. So if I take the radical center as the center and the radius as the length of tangent and draw a circle, I get a circle in this form. Is how we get the circle. Now this property which we identify here is that if this point which I take as C and this I take as A, B and C, I clearly identify that C is the radical center. and my CA, or let me take this as P, is my radical center, and my PA, which is equal to PB, which is equal to PC, are nothing but the lengths of tangents from radical center to any circle. Now this is the length of tangent from radical center to any of the circle, which is same, equal, equal, and equal. Now if I take the radical center as center of circle, and if I take the radius, so if P is the center of circle with radius PA or PB or PC, because all are same, then I get a circle which is said to be orthogonal to each of the circles. The property is that if I take a circle with radical center and radius is length of tangent and draw a circle, that circle will be orthogonal to this, this, and this. That's how we identify the geometrical property connecting with radical center and length of tangent. Thus, then that circle cuts all the three circles, all the three given circles orthogonally. That's how we understand the property. The circle with radical center as center of circle and radius as length of tangent will cut each of the circles at 90 degrees. So now that we have discussed in the previous session about the radical center and length of tangent connected with a circle, if suppose I have the question where I need to find the circle which is orthogonal to the given circles, then definitely this is very much connected to the previous session. If I want to find the circle which is orthogonal to the given circles, it is very simple that I find the radical center and I find the length of tangent and I get the circle with center and radius. So let's see how we can do that using the previous session. So let's take the problem which says, find the circle or the equation of the circle which cuts each of the circles, say initially x squared plus y squared plus 3x plus 2y plus 1 equal to 0, and next x squared plus y squared minus x plus 6y plus 5 equal to 0, and thirdly x squared plus y squared plus 5x minus 8y plus 15 equal to 0. Orthogonally is the question out here. So I have to find the circle which cuts each of the circles orthogonally. So in this case, we have already discussed that if I have three circles, say circle 1, which is this, denoted by S, S dash, and S double dash. So if this is the first circle, S equals 0, and this is the circle S dash equals 0, the second circle, and I have one more circle that is S double dash equal to 0, that is the third circle, then I have to find the equation of the circle which cuts each of the circles orthogonally at 90, 90, and 90. So we know that there's only one circle which cuts each of them orthogonally, whose center is radical center of these three circles, and its radius is the length of tangent from any of the circle. So if I can find the radius, or I can find any of this radius from here to here or from here to here, then I can find the length of tangent, which is the radius, and the center of the circle, which is the radical center, and then equation of circle is obtained. So let's see how we can do that for this problem. So in order to find the radical center, my target is to first find the radical center and the length of tangent. So in order to find the radical center, I find the radical axis of this and the radical axis of one of them here, and then the point of intersection of the two radical axes gives me the radical center. So it is your choice whether you take the pair of these circles or these circles to find the radical center. So I'll be taking first this or this in finding the radical center. So initially my radical axis for s equal to 0 and s dash equal to 0 is what I'm going to find initially. So how do I find the radical axis of these two circles? We clearly know that the radical axis is given by s minus s dash equal to 0, where s is this and s dash is this. So s minus s dash implies this minus this gives 3x minus this 4x plus 2y minus 6y is minus 4y plus 1 minus 5. Therefore, this on further simplification gives x minus y equals 1, which I take as equation 1. So one of the radical axes of s and s dash is given by equation 1 as obtained there. Similarly, I would like to find the radical axis of s and s double dash, which would be equation 2. So finding the radical axis and s double dash, s and s double dash is nothing but s minus s double dash equal to 0. So this on subtraction gives me the radical axis of this and this, which is nothing but here, as can be seen in the diagram. So as we know that s is here and s double dash is here, when I subtract 3x minus 5x gives me minus 2x, and 2y minus of minus 8y, which is plus 8y, gives me 10y, that is 1 minus 15, which gives me minus 14 equals 0. Now this is equation 2 when I simplify this more further. That implies I can write this by dividing the whole equation by minus 2. I get this as x minus 5y equals minus 7, and this is equation 2, which is nothing but the radical axis of s and s double dash. Now the question comes on finding the radical axis, which is nothing but the intersection of this radical axis and this radical axis. So solving 1 and 2, I get the point of intersection C through the elimination method. Now let's find the radical center by solving equation 1 and equation 2. So solving this using the elimination method, I subtract so that this gets cancelled and I get 4y equals 7 plus 1, 8. That implies y equals 2. And when y equals 2, substituting in 1, I get this to be x minus y equals 1. That implies x equal to 3. Therefore, y is 2 and x is 3. And therefore, radical center denoted by C out here is given by the coordinates 3, 2. Is what? we get the radical center is given by 3, 2. So now that we have got the radical center, which is 3, 2, will act as the center of the required circle. Now next comes in finding the radius. In order to find the equation of the circle, we need the center, which is already known, but the radius, which is unknown. So therefore, as we have seen in the previous session on the geometrical properties, radius is nothing but the length of tangent from center to any of the 3 circles, because it is the equal distance from each of the circles. My radius which is length of tangent from C32 to say I take S equal to 0. I take the first circle, that is S equal to 0, which is nothing but, if I take this as A, B, C, then this is nothing but CA, which is given by the formula root S11. Now this is strictly from the formula which we have on finding the length of tangent, which is given by root S11. So how do we find this? Using the formula. Root S11 is nothing but substituting this point in the circle. That is, in place of x, I put 3. In place of y, I put 2. So this reduces to x squared, which is 3 squared, plus y squared, which is 2 squared, which on simplification gives 9 plus 4 plus it is 9 plus 4 plus 1, which is nothing but is 3 root 3. So the radius of the required circle is 3 times root 3, and the center of the required circle is 3, 2, and the radius is 3 root 3. So using the radius and center, we can now easily find the equation of the required circle. So therefore, for the required circle, the center is 3, 2, and radius is 3 root 3. Therefore, equation of circle which is orthogonal to all the 3 given circles, that is, equation of required circle, is given by x minus 3 whole square plus y minus 2 whole square equals r square. Now this is the formula. When center and radius is given, we have x minus a whole square plus y minus b whole square equal to r square, which on simplification gives x squared plus 9 minus 6x plus y squared plus 4 minus 4y equals 27. And this on further simplification gives x squared plus y squared minus 6x minus 4y plus 13 minus 27, which is the required circle in the general form of representation. So this is how we find the equation of a circle which is orthogonal to all the other 3 circles, by finding the radical center and the radius, which is the length of tangent. So geometrical property helps in finding a circle orthogonal to all 3 circles using the length of tangent and the radical center of radical axis.